Hi guys, welcome to Safi Mixed. In this video, I discussed the scenario of agreement and disagreement of quantum and classical results of a physical quantity. There are some situations in which the classical and quantum measurement of a quantity agree directly with one another. However, in many other cases, the reverse is also true. That is, the measurement in the two domains may not agree with each other under certain conditions. To make this statement convincing, I want to provide mathematical proof to both of them through an example. Since I have already discussed the classical and quantum approaches for the solution of the problem of particle and infinite potential well, I prefer to benefit from the results of those lectures in proving these two statements. To this end, I want to compare the quantum mechanical expectation value of position of a particle in the standard infinite potential well with the result of its classical value. We know from the video part 1 on infinite potential well that the classical average value of position is given by the average of x through classical approach equals a divided by 2, where a stands for the width of the potential well. Similarly, we found in the same video that the average value of the square of position is given by average value of the square from classical approach equals a square divided by 3. If you don't recall these results, better watch that video again. Now, I want to find the values from quantum mechanical approach. We know that for standard infinite potential well, the wave function is given by this one relation, where x is the instantaneous position of the particle inside the well, n is quantum numbers starting from 1 goes to infinity, and a is width of the potential. We further know that the expectation value of position is obtained by sandwiching the position operator between the conjugate of the wave function and wave function and integrating over the whole space. That is, we can write this as integral from 0 to a psi steric in x times psi n of x integrated with respect to. Since for standard infinite potential well, the wave function is real, therefore taking the conjugate of the wave function is in fact meaningless, but still we follow the standard procedure. If we substitute the values, I can write the expectation value of position into this one form, where I have just substituted the values for psi n steric of x and psi n of x. Then combining the square roots with two terms, I can write that out of the integral in the form of 2 divided by a, and multiplying the two sine function with each other would make it sine square in pi a times x times x. And using the trigonometric relation sine square x equals 1 minus cos 2x the whole divided by 2, I can reduce the integrand into this one form. Now, opening the brackets, I can write the integral into two parts. The first part contains only position, and the second part contains the product of position and cos function. So it is straightforward to prove that the second integral goes to 0 and the first integral reduces to x squared divided by 2a with limits from 0 to a, and putting the values, I can reduce this to a by 2 like I'm doing in the two steps. From equation 1 and equation 5, we see that the expectation value of position in the two domains agree exactly with each other. That is, we can write the expectation value through classical approach equals a divided by 2, and the same is equal to expectation value obtained quantum mechanically. Now the question is the same true for the expectation value of the square of the position? To show this, let us find the expectation value of the square of position quantum mechanically. I repeat the same procedure, the only difference is that I am putting x squared between the conjugate of the wave function and wave function. And substituting the value, combining the square roots with the two terms, I can put the integral into this form. 2 divided by a into integral x squared times sine square in pi divided by a times x dx. Again, using the same trigonometric relation, I can put the integral into this form, and then writing into separate integrals, I can put it into this one form. Now, without going into further calculation of these two integrals, I just want to write down the results of the two integrals. The first integral gives a squared divided by 3, and the second integral gives a squared divided by 2 times n squared pi squared, which by taking a squared divided by 3 common, I can further write it into this one form. That is a squared divided by 3 times 1 minus 3 divided by 2 times n squared pi squared. We see that equation 6 does not agree with equation 2 for all values of the quantum number n due to the presence of the second term inside the brackets. However, for n tends to infinity, the second part inside the brackets of equation 6 goes to 0. Under this condition, the quantum mechanical result exactly agrees with the classical one. So for large value of quantum number, the two results agree with each other. And this is the reason we usually say that the quantum mechanical results of a particle reduce to the corresponding classical results in the limit of large values of quantum numbers defining the problem.